To be an introductory course on renormalization group. It's a big field, and so I'm just going to scratch the surface. And if you want any, well, it's not going to be a mathematical course. I'm not going to give you any theorems, just a philosophical picture, and that's it, okay? And if you want to have any more details even behind this philosophical picture, there are lecture notes on the website. You go there and you click and you find it. And the lecture notes also include exercises, and there is even a TA. Joona, can you put your hand up? Who can help you with an exercise?
What's his name?
Joona Oikarinen. All right, so without any more on that, let me just go to what I'm going to talk about. And let me start with, I'm basically going to talk about interplay between two different things which I call quantum field theory, and the other one is statistical mechanics, okay? And let me start with an overview before I go to any details. So in the quantum field theory, we are talking about fields which are actually random fields defined in continuous space. And then there is some probability distribution on these fields which we write in the following form. And every time I have this phi, which is actually in LaTeX, it's var phi. Okay, var phi is going to be continuum object, and in statistical mechanics we are going to have phi's. Okay, so don't get confused with these two things, because we are constantly going to go between the two things. So phi will be also a function of x, but x is now in lattice ZD. Okay, and there is again a probability distribution, which that time I will call with an h. Okay, and these formal objects will be clear in a moment, but at the moment you're supposed to think about them in terms of there's an S and an H, and the S is called action in the quantum field theory, and the kind of action we are going to deal with almost actually only this action and nothing else in this course will look something like this. Okay, it's an integral of certain local function over phi. And on this side, we call this H Hamiltonian, or energy. And it has exactly the same form, except that it's a sum over the lattice. And there's instead of a continuous gradient, there's a discrete gradient. And I will call these variables here slightly different. I call this piece r, and then the other piece lambda. Okay?
You're missing a phi squared in there, right?
Phi squared. Ah, that's missing. Okay. Okay. All right. What is this about? This is for us. This continuum, this quantum field theory, is going to be sort of a model of that. It's going to be what's usually called scaling limit of statistical mechanics. But of course, its main use is somewhere completely different, namely in quantum theory, quantum mechanics of infinitely many degrees of freedom and elementary particle physics. I'm not going to go to that. If you're interested in the lecture notes, there's a lot of discussion about that, but you can ignore it if you wish.
Tell us about d phi.
And d phi I'm not going to tell you about. I'm going to tell you about it in a moment. At the moment, you just think about that these probability distributions are weighted by such objects. Okay? And on this side, we are talking about phase transitions. In statistical mechanical systems, and something which is called critical phenomena. What are the problems here? On this side, the problems. This was not part of the business at all. Okay, This on this side, I will call the problems ultraviolet. Ultraviolet refers to very short wavelengths, namely short wavelengths, and this means sort of locality. This function phi is not really a function. It will be a divergent object. For instance, its variance will blow up. And on this side, we have a problem which usually is called infrared, namely long wavelengths. And that means that if I'm looking at correlation functions like this, how these objects are correlated at different points in my space, then this is going to have very long-range correlations with some power law correlations. Okay. So these are problems for which it took physicists a long time to figure out how to deal with, and sort of the modern theory of how to sort of understand this business goes under the name renormalization group, which I just call RG. That's the topic of this school, and the idea here, in a nutshell, and this course is going to be about, is that instead of talking about this immediately like that, you sort of start talking about some sort of things which let me call it effective theories. Okay, namely not talking about the problem under all this is scale invariance. There are lots of different, as you see here. This is a scale invariant function in the points. So one discusses things scale by scale, and one instead of talking about this weight, you talk about weight, which is describing the system for scales bigger than something. Let me call the something epsilon, which is varying. And in the same way here, I'm talking about the distribution function of the system for scales bigger than, well, let's put R here, bigger than something. Okay? And then the renormalization group is trying to understand how these objects change when you go from scale to scale. So you take as epsilon, so you know how things behave up to scales epsilon, and then you want to get rid of some of them, go to 2 epsilon, and this map you call the renormalization map. And on this side you will have similar thing. And instead of trying to understand this, which Prof was asking, what is this here? You're trying to understand it piece by piece by going scale by scale. So, for instance, multiplying it by 2. So that's the no, bigger than HR has infrared cutoff R. This has ultraviolet cutoff epsilon. It will be clear in a moment. Okay. Is it okay? Now let's one more thing. So the end result of that analysis will be something which is called universality. Namely, there are very few limits. And that then explains in the statistical mechanics side that many systems in real nature have similar behaviors when one looks at them at the phase transition points. And on the quantum field theory side, it says that there are only very few quantum field theories. Okay? Very few consistent ways of making this fields which have such a distribution. Okay, so that's the overview. Okay, so let's go to the setup. Okay, so that's Pronob's question. What are these objects here? So in quantum field theory, in the end of the day, as I told you, the object is not really a function, so it will be a distribution. And by the way, I have no idea. There probably is a huge spread of background. So if there is anything unclear, please ask. Okay, but in this case, let me just think about them as generalized functions, distributions taking values in tempered distribution, and so in principle only once you smear them with functions you get well-defined random objects, and I'm using this notation for the pairing of the distribution and the test function, and just think about it the usual way. Okay. And in statistical mechanics, it's the same thing. This phi, except that now it's in the little s prime of ZD. So these are functions on the lattice which decrease can decrease polynomially at infinity, and then phi of f is sum over x in ZD, phi of x, f of x. Okay. Okay. Measures. These probability distributions are measures on these spaces, and again, I hope you have some background on that. If not, in the lecture notes there's a long discussion of this, so you can look at that. But basically there's a one-to-one correspondence between such probability measures and their Fourier transforms, which I denote by W, and that's just the expected value. Well, let me write it like this: integral of e to the I phi of f d mu phi, the generating function. And the one-to-one correspondence goes under the name of Milnon's theorem. We are not going to need that very much, because in the end we are going to almost only have measures defined on Rn actually once we have cutoffs. But let's have that. The interesting set of such measures are Gaussian measures. Where this W of f is actually exponential of a quadratic form. And let me write the form like that. And in the cases we are interested, well, this quadratic form is called covariance. And in the cases which we are interested, this is just given in terms of integral kernel. So integral f of x, f of y, c of x, comma y, dx dy. And in the lattice case, in the same way as a sum. Okay.
F is a Schwartz function.
And f is a Schwartz function here, so f belongs to S of f, or little s of S of RD ZD. Okay. And the thing about Gaussian measures, which, well, okay, then still some terminology. We talk about correlation functions all the time. Correlation functions are just expected values, and I'm actually going to use this notation for the expected value almost all the time. It's more convenient than the E. And they are So they are the averages in that measure. And in the Gaussian case, then they are just given by an explicit formula, namely the covariance determines everything. And let me write it like this. So endpoint correlation function is given in terms of products of two-point correlation functions, and you sum over all the ways to pair these n points here. So Pn is pairing of n objects, little p is a particular pairing, and then you have this product here, and that's given by the weak formula. So if anything of this is unfamiliar to you, look at the lecture notes and have it there. Okay, so that's the setup. Okay, so examples. Still in the setup. So there's the Gaussian free field on GD. Okay, so here I take the covariance, the inverse of this operator, where Laplacian is the discrete Laplacian on the lattice. So it's given by sum over f of x plus y minus f of x on the lattice. And in that case, the covariance is translation invariant, so I'm just using it the following notation with abuse, just like that. And it has a concrete representation as an integral over a compact region minus pi to d in terms of Fourier transform. Okay.
Is that an R in the minus Laplacian plus R, or is it?
That's the R, the same R as here. Is it? My R doesn't look like an R. Supposed to be.
I thought I saw an m squared in the continuum.
Yeah, but here I'm on the lattice. You remember?
Okay, I've got it.
R on the lattice, m squared in the. Okay. Phi and var phi. I mean, we are going to go in this. So this is just the Lebesgue measure divided by 2 pi to power d. All right. So and mu p are the eigenvalues of the Laplacian, which are given by 2 times sum over 1 minus cosine p alpha, where alpha runs from 1 to d. This is the scalar product in Rd. All right. So that's the Gaussian free field on the lattice, and the Gaussian free field in the continuum is more or less the same, except that it's in the continuum. So it's the same C, except that now it's Laplacian on the continuum, and there's the mass. Sorry. Okay, so C is minus that, and Cx minus y is now the same integral, except it's over Rd. Okay. Okay, so what are the interesting things about these things? So let's look at the infrared first. Well, the infrared is the following. This correlation function, so this is really the expected value of phi x and phi y, okay? So in the infrared, this phi x, phi y, in the statistical mechanics thing, this behaves as x minus y goes to infinity, like a constant times e to the minus x minus y divided by some psi, where psi is usually called correlation length. So it tells the length how these are correlated, and psi depends on r, and it's an easy calculation for you to show that it goes like square root of r, 1 over square root of r. So it goes to infinity as r goes to 0. Things become strongly correlated, and when r is 0, it goes like 1 over x minus y to the power d minus 2. Except in 2 dimension where it goes like log. All right, so in the ultraviolet, we have sort of the mirror image of this same behavior. So this goes like constant over x minus y to power d minus 2 when x minus y goes to 0. Okay, so the thing blows up, and in particular this is just the example of what we had before, namely the field itself is really not a function, but its variance is infinite. Okay, so with these 2 examples I can illustrate the scaling limit. Okay, so what is this? This is really, as I told you, it's supposed to describe the statistical mechanics. And let's make this following change of variables. So let me call var phi and put an epsilon there, and define it to be the following thing. Namely, I multiply it by a blowing up factor, and I take the lattice guy and look at it at very long distances. I'm going to think about epsilon going to 0. So I take my lattice field, look at it long distances, and multiply it by a blowing up factor. Well, it's a simple computation to then compute this. Okay, from that, by a change of variables in this integral, you plug it in, you get basically integral from minus pi over epsilon pi over epsilon e to the I p x minus y 1 over epsilon minus 2 mu epsilon p plus r over epsilon squared. Okay, so I just put here the x minus y over epsilon, make a change of variables p going to epsilon p, and took this factor which was carefully manufactured to get such a form. So here you see that when epsilon is going to 0, this is picking up just the behavior of the mu. So this looks like p squared plus order p4 when p goes to 0. So this is just picking up the behavior around 0, the p squared. That's multiplying by epsilon minus 2, everything goes right, and we see 2 things here. If r is 0, then this phi epsilon seems to converge to the g of f in continuum. The integration goes over rd, and you get p squared there. And when r is non-zero, so if I take r, let me take r here proportional to epsilon squared times a number, which I call m squared, and then again it goes to g of f. And here 1 over minus Laplacian plus m squared. So we see that if we are looking at the statistical mechanics at the critical point, the one where correlations decay polynomially, and we scale, look at it at long distances and rescale, we get quantum field theory. Okay? And if we do it at the critical point, we get the scale invariant quantum field theory, something. This, of course, is exactly given by some d-dependent constant divided by x minus y. That's the Coulomb potential. Get the scale invariant quantum field theory. And if we sort of scale, go to longer distances and rescale, simultaneously go towards the critical point, namely m squared is fixed and let r going towards the critical point in a well-controlled way, then we get non-scale invariant quantum field theory, namely the one which has a length scale in the mass squared here. So this is the simplest case of a phenomenon which we are going to be interested in. Okay?
You take var phi or phi in the definition of phi epsilon?
I call it var phi because it's now on an epsilon lattice. Okay?
Okay. Right. Okay.
There's a slight ambiguity in the notation, but it should help you to think about it, that it's something which wants to be a quantum field. Okay? Okay. So that was the setup. Okay. Then the model we are going to. In this course, I'm going to discuss only one model. Okay, and it's the Ginzburg-Landau model. It's called the Ginzburg-Landau in the statistical mechanics, and in the quantum field theory, it's just called the phi 4D model. Okay. So what is here? So let's again start with the statistical mechanics side. So we are looking at measures, and let's now really go to. Okay, let me first write. Okay. So this is for the phi. This is statistical mechanics. Let's look at the following probability measure. And there is a Hamiltonian, there's a phi, and there is a d phi. Lambda is a set in RD, so box, for instance, in ZD. Okay. Put it in a finite box, and this is a Lebesgue measure here. Lebesgue in r to power lambda. Okay, and then I have the Hamiltonian. So I'm thinking about a finite volume, and this is just sum over x now in lambda, the same action we had Hamiltonian we had before, with a discrete gradient squared plus r over 2 phi x squared, and then I add here this lambda phi x4.
So maybe you should change the lambda as an element of ZD to lambda as a subset, as a compact subset of ZD.
Yes. The subset in ZD. Okay. And we are interested in the thermodynamic limit, namely in the limit when lambda becomes everything of these measures. Okay. And when I put this little lambda to 0, then that's back to our old GFF. And you can recognize it sort of here by writing this as phi minus Laplacian phi plus r phi half. And let me put here that, of course, since I'm in a finite box, I had to fix some boundary conditions. I'm not going to discuss those at all, but just think about it periodic, for instance. Okay, so that's that. So what is the question here? Okay, you construct first this limit, and then you ask the following question: find a critical parameter value r depending on this lambda. Okay, so try to find an r such that the correlation length is infinite. We know a solution to this when lambda is 0. That's just 0. Okay. And then the second question: find a parameter. Well, let me call it just a, so that at the critical point this decays. Well, plus little o of 1 over x minus y to the power a as x and y go to infinity. And again, we know that a at lambda equals 0 is d minus 2. Okay, that's the question of critical phenomena, sort of the first question you wish to understand. In the quantum field theory case, you have the following. So let me take a measure d nu. Let me call it nu and not mu, so to sort of think it's different setup. I put an epsilon and lambda here, and I put the var phi. And again, it's 1 over z e to the minus some action. Let's put the epsilon and lambda and var phi and d phi. Okay, and now this is Lebesgue in r to power lambda divided by epsilon to power d. And what is my action? Well, it's the same thing. Integral half gradient phi squared plus r over 2 phi squared plus lambda phi 4, where the integral is a Riemann sum. So now I'm thinking about box lambda and a lattice again, where the lattice spacing is 1 over epsilon, is epsilon, and discrete gradient is now the lattice gradient. So phi x plus epsilon. Sorry, var phi minus over epsilon. Okay. So I put it on a finer and finer lattice, and then we are asking about the question: do such limits exist? Namely, you take the thermodynamic limit, and you take the epsilon going to 0 limit.
So you want epsilon or epsilon to the d times z, epsilon.
I think it's lambda over epsilon.
Which one?
Under the sun.
Yeah, I'm using a lazy notation. Okay, so let me put it like that.
I still don't like it because that's a really large lattice, isn't it? Don't you want
Yes, you are right. Yeah. Okay, that was your problem. Okay, so then I can even take this away.
Do you want an epsilon to the d as well?
No, he wants to.
Yes, that's what I was missing, the epsilon to d here. So I have a Riemann sum instead of an integral. So volume element is epsilon to d. I'm summing over fine lattice. That's my integral. And then the only thing which is missing is that this is the discrete gradient. So I could even put an epsilon here if I wanted and call this epsilon. Okay. All right, so that's what you would like to know. And there is a connection between these two questions, of course. Namely, it's just the same change of variables which I had before. So I put var phi and put it as epsilon d minus 2 over 2. That's of this phi. Sorry, phi is epsilon d minus 2, that at epsilon x. Okay.
Maybe you should also put some epsilons on the phi's in your formula for S.
No, that I refuse to do. But you can do it if you want.
Okay. Yeah, but they are phi epsilon.
It's a dummy variable, which is integrated over. So I don't have to put anything on dummy variable. I can call it whatever I wish, but I call it var phi because I want to remember. Okay? But you can put it if you want.
I thought you might want to put it on and then...
No, I don't want to put it. I want to distinguish between... yeah, okay.
But then, I mean, then your problem is that your formula for H won't be right unless you put some phi epsilons in it.
Well, let's see. Let me write my formula for H, and then let's see if you think it's right or not. Okay. So S epsilon. Here is a correspondence, and S epsilon lambda var phi. If you make this change of variables, is the Hamiltonian at lambda over epsilon. Okay. And then I have phi, and then I have epsilon squared times the mass squared. Well, let's put here mass and g. And here, now I know why you don't like it. I mean, this has to be m squared all the time. Yeah. Okay. And epsilon 2.
It's lambda.
Well, I hope not.
No, not yet.
I hope not. I hope not. Okay. So these are two different things. Okay. Here I'm a definition of Ginzburg-Landau model, parameter r and lambda, definition of a cutoff quantum field theory with a mass parameter m squared and coupling constant g, and the connection between the two is the change of variables, like that, and then the m squared. If I have an m squared and g, then here I have epsilon squared and epsilon to 4 minus d. This is just plugging in and making the change of variables. I'm not going to do it. You do it yourself. These are called the canonical dimensions. Of these parameters, okay, if you read the physics book. Okay, so if I want to understand the quantum field theory with these parameters, I have to understand the statistical mechanics in a really big box, divided by epsilon, with a really small mass parameter and small or large g, depending on whether the dimension is less than 4 or bigger than 4. Okay. I think I need the eraser now. Any questions so far? So far we haven't done almost anything except introduce phi and var phi. And the very important connection between the two. Okay, so what do I want to do next? Well, let me just finish this story and say that, so I told you in statistical mechanics the question was to find the critical point, right? R as a function of lambda. What is the question here? Well, the question here is, does this limit exist? And the answer is no. D less than 3, you have to change a little bit for the limit to exist. You have to replace this mass parameter by adding to it something. Let me call it A epsilon, something depending on the epsilon. And then what the A epsilon depends on the dimension of your universe. So it's given by some, let me call it, say alpha 1 times g times log epsilon. If the dimension is 2, that's some alpha 2 g 1 over epsilon plus alpha 3 g squared log epsilon. The dimension is 3. Okay, and if the dimension is 4, there are no interesting solutions. But we'll come back to all of that later. But the question here in the quantum field theory turns out to be that you have to modify it. In the statistical mechanics, you are just trying to find a very particular parameter. In the critical point in statistical mechanics, you have to make sort of re-understand what you mean by this kind of action function. When you, in physics, you end up writing something like that, then it turns out that the parameters there have to be sort of understood slightly more than what you thought in the beginning. Okay, so, but we'll come to that later. What I next want to do, I want to really scratch the surface of a big topic, namely perturbation theory. Again, if you really want to read about it in this context, there's a long story in the lecture notes. But what do we want to do? We want to compute these correlation functions, okay? So for instance, in statistical mechanics, in both cases, so endpoint correlation functions in statistical mechanics. So let me put here the parameters we're interested in. So in some finite volume, and let's put this coupling constant. That's an interesting parameter here. We want to vary the coupling constant, and in the quantum field theory, similar things. Here I have epsilon and lambda, and well, okay. So they are given by these finite dimensional integrals. So it's a very simple exercise to show that these are smooth functions at origin. Okay. So what is the perturbation theory? It's just a Taylor series. Okay. So let me do it in the statistical mechanics setup. So let me call this measure mu lambda is 1 over z normalization factor to make it a probability measure, and let's put e to the minus lambda h of phi, and let me do it in the case where I don't even have the r parameter, so I had really simple things. So let's put here r equals 0. Okay, so h of let me write it like this. Sorry. So e to the minus lambda times v d mu c of t. So v here is just sum over x in lambda, p of x4, and that's the Gaussian measure with covariance c. Okay, no, I'm not even going to put r to 0. Let me just take d mu c. G of f covariance 1 over minus Laplacian plus r. Okay, let's keep it there. Okay, so that's just rewriting what we had here, somewhere here. Okay, I took the quadratic part separately. I call it the Gaussian measure, and then I have the perturbation. Okay. Okay, and let's take some observable depending on phi, and we want to compute this in that measure. Okay, so let's put Well, that's a simple thing to write. So it's dd lambda integral f e to the minus lambda v d mu divided by integral e to the minus lambda v d mu. And once I differentiate, I get two terms, it here. And so let me write it in the following form. I want to write it as expected value of this minus this. The two terms. And let's give it a name, minus f semicolon v. The semicolon refers to this subtraction here. It's called truncated expectation. Truncated expectation, or it's also called the cumulant. Okay. Obviously, you can sort of keep on differentiating, and you get similar but more complicated terms. Similar but more complicated terms. So if I take the nth derivative of this expected value of f, then it's just going to be minus 1 to power n, because there was a minus sign, and then something which I will just call f semicolon v semicolon v semicolon v. Okay. And it's your challenge to find a formula for that, but this looks like something like that. There is an f v to power n minus n times f v to power n minus 1 v plus lots of terms, okay? And just differentiate, okay? In probability it's called a cumulant, and I'm using the physicist notation semicolon for it. We are not going to, you will find a lot of stories about that in the lecture notes, but we are not going to need very much of this. Let me just write it to you in the simplest case, which we are going to compute a little bit. So let's take the example. So when f is phi x and phi y, and I want to compute. So what do I get? Well, first I get, let's put the lambda here. First I get just phi x and phi y when lambda is 0. That's the first term in the Taylor expansion. Then the first non-trivial term is proportional to lambda. And the v was sum over x, so let's just write it sum over x, x1. And then there is a phi x, phi y, semicolon, phi x1 to power 4. Okay? And let me write one more term, plus lambda squared over 2, sum over x1, x2, phi x, phi y, semicolon phi x1 squared, fourth, semicolon phi x2, 4. And then plus order lambda cubed. We are going to discuss these terms a little bit. First of all, it's convenient to introduce a little bit of notation and to think about what these are, okay? So I wrote you the formula here. You remember in the Gaussian integral, all correlation functions are sums of pairings. So if I didn't have that, I would just have to pair 6 points. There are 4 sitting at 1, and then these 2. And with that, I'm supposed to subtract pairings where I'm only pairing this group within itself and this group within itself. So it's obvious that this term then contains only pairings of that group to that where at least one pairing between the two groups exists. So let me write it in terms of nice notation. So that's the first term, then minus lambda. The second term looks like this, and then the next term looks like this. I need some space. Okay, so there are lots of pairings, and once you do the numbers, you get the following: 144, 48, and then one more, 96. Okay, and what do I mean by this? Yes?
Some numerical factor in the second term as well?
Yes. All right. Okay, so what I'm supposed to pair, this is going to choose between 4 and this going to 3, so 12. Thanks. All right, and what do I mean by this? Well, let's just look at one term which we are going to discuss in detail for the next half an hour. This one. This by definition is just that you have c of x minus x1, c of x1 minus x2 cubed, and c of x2 minus y. And you're summing over x1 and x2 in lambda. Okay? I think once I wrote this, you can write formally for all the others. Well, let's just, for the fun of it, write this. So this equals c of x minus x1, c of x1 minus y, and this bling here is just c of 0. Okay? All right, you can of course do the combinatorics for the general term. These terms are called Feynman graphs. The combinatorics can be done elegantly, etc. I'm not going to go to that, of course, in such a short course. I'm just going to discuss a couple of these terms to illustrate what happens in these two problems, namely the infrared and the ultraviolet problem. Maybe go here. Is it so far so good? There's the question, yeah.
So, maybe two mathematical question. How do you know that it's going to be C infinity?
How do I know what?
How do you know that it's really C infinity in lambda, this thing?
This is finite dimensional integral. Remember?
Oh, okay. And
it's a nice, simple exercise, okay?
okay.
And if you are unable to do it, it's in the lecture notes.
Okay. And the other question is, those constants that you're writing there, they look like they are growing like crazy.
Which constants?
The 144, the 90.
Yes. This perturbation expansion will be strongly non-convergent.
Oh,
Yes, it will be. In the end of the day, once all the dust settles, it will be an asymptotic expansion. It will be a Taylor series of the C infinite function in the end of the day, but the day is long, okay? Okay, maybe I can at least start with the infrared problem before the break. Okay, so the infrared problem. Okay, so of course, if R is positive, then this limit let's just consider any of these individual terms, okay? So I'm going to, in particular, discuss that particular graph here, which I wrote. All these sums are, of course, finite, so it converges trivially. But since C was exponentially decaying, basically something like this. These sums actually have a limit as lambda goes to ZD. So that individual terms have limits as lambda goes to infinity. But let me just take the limit without any further discussion, and then let's write what this particular graph. So let's discuss this. Yes.
Square root should be on the upper side, on the numerator.
Yes. Good. So let's call this something. Well, all these graphs are actually of the following form. Once you keep on writing them, there is always something starting from x, going, and then some junk, and then going to y. Okay. So all these graphs, everyone, even if I keep on doing it, it will be, so the 2-point function, let me call the 2-point function g2 x and y is this phi x, phi y, lambda. This will be of the form in this expansion. It will be of the form if I write its Fourier transform. Then what is this? This is a function c of x minus x1. Then there is some kernel which will be by translation invariance only a function of the separation. And this is a convolution of one function with a second with a third. So its Fourier transform is a product. C hat of p from here. Then k hat of p, let's put it the other. C hat of p, k hat of p. Okay? But remember how what is c hat of p? This goes like 1 over p squared as p goes to 0. So c of hat p of squared goes like 1 over p4. This is not an L1 function. So we miserably fail if we take r to 0. Okay, this is at r equals 0. If I take r equal to 0, then I have this singularity here, and every term on my perturbation expansion is ill-defined. Now, this is silly, of course, because what was our question? Is it erased? The question was that I'm supposed to find r critical of lambda, so that I have a critical point. So instead of looking at, I should do the following. I should, when I'm discussing the r equal to 0 limit, I should, instead of looking at lambda phi 4, I should look at r critical of lambda half times phi squared plus lambda times phi 4. So I'm supposed to find this so that my correlation functions are critical. And we could, of course, now try in this perturbative scheme to find it as a power series of lambda. Just formal power series, okay? Okay, so how would that go? Okay, if I change this to that, then I get, of course, additional graphs from here. I will get also graphs like this, where there is so this would be c of x minus x1, c of x1 minus y, and then this r critical of lambda. on top of the ones I had there. Okay? So it's obvious what I should do. It's obvious what the R1 should be. It should be just the one which I forgot there, the minus 12. So I should take R1 plus 12 times, no, minus 12 times lambda times what I have there, namely C of 0. Okay? If I take that, then what happens is that this guy will exactly cancel the one which I had this second graph there. If I do that, then I cancel. And in fact, if you look at it, you will also cancel all the others, and you end up with the 2-point function being of the following form. This minus, what was it, 96? Plus lambda squared, 48 lambda squared, times this, plus order lambda cubed. If you do that, you get rid of this problem. Okay? So this first graph, which was infinite in the limit of r going to 0, disappeared, and I have a nice expression here. Now you ask, of course, what is this? This will still have the same problem as before. And I think we're going to have a break, and then we're going to discuss this graph. So this will be what to do with this. All right? Okay, then let's have a break.
Thank you.
Are there more questions? Okay, if not, there is a coffee break, and we resume at 11:30.